Welcome to the explainer video of Odin's Technology Set. In this video, we will explain the tools behind our solutions and give you an understanding of the mathematics and statistics. Who is this video for? This video is intended for the plant staff, operators, reliability engineers who are interested in understanding how we raise alarms and predict failures. Also, maintenance staff can see how we provide root cause investigation support for the daily work, improve planning and scheduling. It's also for the risk engineer at the insurance company who wants to become familiar with predictive maintenance and the technology behind it. The agenda is that we're going to start the presentation with some definitions. We are going to look at the tools presented through the problems we want to solve. That means we're going to start with too many alarms are being released, the failure prediction, and the root cause investigation. We will also answer two of the most common questions that we get when presenting Odin. At the end, we will summarize the takeaways. A short word about myself. My name is Casper Schneeberger. I am the CEO of Odin. I worked as a maintenance consultant, optimizing processes and organizations carried out throughout the world, from Flint, Michigan, USA to Jönköping, Sweden, mostly for chemical and petrochemical plants. Let's start with the definitions. Abnormality. In our context, is an outlier. An outlier can be defined as a breach of a threshold of allowed or expected signal behavior. Abnormalities are not explained through trends and also not through seasonalities in the data set. So we end up with the two dots highlighted in the blue here. Cluster. A cluster is a group of signals that is behaving in a statistical similar fashion. As you can see, we break down the movement of all signals into subgroups we call, for instance, cluster 1, cluster 2, cluster 3. Threshold. A threshold is defined upper and or lower limit for a specific signal measurement. The risk score is defined as the magnitude of abnormality or breach of threshold, indicated here by two risk-scored outliers, 42, 61. Another important definition is the failure tree. A failure tree is a top-down methodology to assess the reliability of an equipment. At the top is usually the top event of interest, here shown to be blaze failure. This event is further broken down into root causes, here shown to be high steam pressure, and root cause number 2, high vibration. For root cause investigation, the reliability engineer needs to know the probability of each root causes contributing to the top event. Another definition is the memory period. The memory period is basically the time interval we apply to our calculations. Depending on the signal statistics, we might want to use shorter or longer time intervals for performing our calculations. So for example, the calculation of the average vibration can be based on short memory period, let's say 1 day, 7 days, or 10 days. Finally, the definition of the ensemble technique. Ensemble, meaning in French together, is a method that takes out output of several models, averages them out, and or checks whether each model individually meets a set of criteria. In the context of outlier detection and prediction, we find that ensemble techniques helps us to reduce unnecessary alarms. For instance, we evaluate the signal movements based on typically 3 models, each based on different statistical dynamic thresholds. So for example, if only 1 out of 3 of these thresholds are breached, then no alarm is released. But let's say we have a situation in which 2 out of 3 models are alarming, then we meet the ensemble critique and release an alarm. The criteria 2 out of 3 or 1 out of 3 can be modeled. Also, the number of models can be different than given in this example. The benefits of this technique is that it reduces variance in the results and also increases the quality of output through averaging out. The downside is that it is, however, computationally expensive to run various models at the same time. Now let's have a look at the problems we want to address together with our Odin solutions. Starting off with the too many alarms problem. Plant operators are equipped with a large set of instrumentation and many control screens. More often than not, the operators have too much information and too many alarms. What tools do we use to increase the quality of alarms? 1. We developed a dynamic threshold that improves upon the existing alarm logic. Static thresholds are usually set at commissioning of the equipment. Especially rotating equipment is quite dynamic and changes its behavior during the time wear and tear, which means that the static thresholds might become outdated and are either too low or too high. Then we rank the outliers with our abnormality score based on the statistical distance to the threshold. This also allows the operators and the plant staff to understand what is appropriate action. Also, we filtered these alarms with the ensemble technique presented earlier. And finally, we tie those outliers to potential root causes via the failure tree. The second problem is failure forecasting. Failure forecasting or early anomaly detection is what the basis is for predictive maintenance. Simply put, the problem, or rather the objective, is to increase the reaction time for early intervention to reduce the damage to the asset. Ultimately, this leads to a faster reaction time and improves planning and scheduling of technicians and spare parts. Now the question is, how do we do that? We currently are employing two types of techniques. One of them is our in-house built heuristic we call the worm. The worm takes its name from the rolling sum of abnormal measurements taken across a time period that is visualized by a red vertical line. The x-axis shows the timeline and the blue y-axis shows the signal measurement value. Now let's look at the challenge. We have a signal measurement that at some point will breach the threshold defined. How can we improve upon the situation where the alarm is released only after the breach of the threshold? We cumulatively sum up all the random movements within the defined memory period and release an alarm once the gradient of the worm increases. Let's have another look and see when and how the outliers predicted coincide with the gradient increase of the worm. This is the actual use case for a steam turbine where we were able to detect outliers on average 6 days before the existing logic. What you see here is that for two outliers, which are forecasted to increase in the gradient of worm, which leads to an earlier alarm and ultimately to advance notice of potential failure. What are the benefits of the worm? The worm is stable, simple, and reliable. But it also suffers from limited and fixed memory period as well as limited and fixed forecast horizon. In order to overcome these limitations, we are employing neural networks. Regular neural networks are not suited for the type of problems we're addressing because regular neural networks are used when output predict is not sequential nor time dependent. Let's have a look at why the time dependency issues requires another type of neural network. Let's say if at T1 we feed an image of a dog to a neural net, and it will identify that image and provide a relevant label to that particular image, say dog. Similarly, if in the following sequence at T2 we feed an image of a cat to the neural net, it will provide a relevant label to that image as well. However, you notice that the new output that we have got, a cat, has no relation to the previous output that is of a dog. Or you can say that the output at T1 is independent of the output at T2. So we can say that in a regular so-called feed-forward network, the outputs are independent of each other. There are, however, situations where we need the output at T1 to support the forecast of output at T2. To illustrate the requirement for time or sequence dependency, let's suppose that there is a text prediction model which is run on the data of a sentence in a book for which we are trying to predict the next word. Assume that we are trying to predict the last word in the sentence, say, the car drives on the road. This situation can be addressed by a regular neural net because the context is quite simple and because the last word almost always ends up being a road. But what if the sentence allows for more options and requires context, such as the car is in a good condition? Then we need to extend the memory and understand the preceding chapters of the book to be able to contextualize the sentence to allow for better prediction of the missing word. In short, the type of neural net we are applying is the LSTM network, which is able to store and memorize information over an extended period of time intervals and allows for sequence dependency. Example applications of this type of networks is being used in stock price prediction, speech recognition, and failure prediction. The benefits of LSTM network is that it has a flexible forecasting horizon, an improved memory period, and is able to model sequence interdependencies. However, it requires deep learning expertise and is computationally expensive. Let's look at the problem and solution that especially concerns maintenance staff, which is understanding the root cause of the alarm. To allow for faster fact-finding, the maintenance staff needs to know what the problem is and what to do about it. Based on our cluster logic, we are able to provide a list of probable failure modes. Together with domain experts, for the specific equipment in question, we map the alarm's signals that are clustered together to the specific nodes in the failure tree for which there is a great statistical match. By doing this, we are able to highlight the nodes in the failure tree that are most probable to cause a problem. Respectively, locate and classify the failure that supports the maintenance staff with reduced root cause finding. Now let's look at the two most common questions we get. How precise is your model? We are able to detect and forecast 5 out of 6 alarms in actual datasets on average 6 days before the existing alarm logic picks it up. Even though we may not catch all outliers, we are able to improve upon the current alarm logic in a real industrial setting. What is the financial benefit? We built a financial model that lends itself in corporate finance and risk management theory to calculate expected reduction loss. Come, find out and get a free ROI estimate. In closing, let's look at the takeaways. We discussed the definitions: abnormality, clusters, threshold, failure tree, and also memory period, risk score, and ensemble technique. We went through the problems such as too many alarms, which we addressed by our risk scoring, dynamic thresholding, and the ensemble technique. We look at the failure forecasting, for which we are doing our worm heuristic and the neural nets. And finally, also the root cause investigation, which will support through our clustering and failure tree matching. Thank you very much for your attention. Feel free to reach out at the given information provided here. Have a great day.